There's been tremendous growth in the demand and use of unmanned systems by the U.S. Navy. The Future Defense Program calls for around $12 billion in funding for unmanned aircraft, surface vehicles, and underwater systems, a number which has been steadily increasing over the last 6 years. The operations, maintenance, and personnel costs are an order of magnitude even higher. For FY 21 to 25, the Navy budget is requesting around $125.8 billion to support these activities. One of the primary factors that's helping to drive up these enormous costs is the lack of automation available in these environments. The current practice of sending out on-site maintenance is not only not scalable, but in many cases unnecessary. One component that currently requires on-site support is the generation of cryptographic keys. I'm here to discuss a novel scheme which was developed in-house at the Naval Information Warfare Center as part of an internally funded research project known as the Dynamic Temporal Encryption Scheme. This scheme has the capability to securely auto-generate encryption keys, which will in turn translate to more secure systems at lower cost. One of the motivating setups for our scheme is a scenario where you have a deployed underwater UAV executing a mission in a tactical environment. Such environments typically have limited to no data connectivity, and oftentimes systems are submerged for extended periods of time. Despite these conditions, there's an operational need to periodically generate cryptographic keys that are used to encrypt blocks of data throughout the lifetime of the mission. Some of the unique challenges associated with such environments include the following. First, how do we ensure there's enough randomness to generate secure encryption keys? Complicating this process is the fact that many systems are loaded from a small set of nearly identical images. Second, how do we devise a scheme that allows us to securely recover our encryption keys without relying, for instance, on a trusted platform module, which may or may not be available on all systems? Our approach relies on three simple components: the mission plan and the UAV sensor data, both of which are used to generate our encryption keys, and a conditionally invertible function that will be leveraged when we want to recover the keys. At a high level, how this process works is that first the mission plan and the sensor data are combined to generate a key, which is then used by a UXS to encrypt blocks of data. Our keys are never stored in persistent memory, and so once the data has been encrypted, the key is discarded. Meanwhile, the UXS continues to execute its mission, and during this process, its sensor data may change from the time at which the encryption key was generated. Despite this change, provided the UXS executes the planned mission, given the mission plan and the current sensor data, our function can regenerate the original encryption keys so the encrypted data can be decrypted. However, if the UXS deviates from the planned mission, and in particular if something more nefarious occurs, such as if the UXS is captured by an enemy, and the current sensor data and the initial sensor data will deviate significantly, and the function previously used to regenerate our encryption key will no longer be invertible. We have implemented the dynamic temporal encryption scheme and software on an Ion Robotics quad rover running Ubuntu Linux. What we're going to show next is an illustration of this quad rover running the DTE protocol, and in particular how the conditionally invertible function discussed earlier works. We've programmed the quad rover to execute a mission which consists of performing one loop around the field shown on the picture to the left. During this mission, the quad rover is maintaining a secure communication session with a local machine, and the session will be illustrated in the second video shown on the right. Included in the second video is the feed from the quad rover's camera. In this scenario, the quad rover updates the cryptographic key used to implement the secure communication session at regular intervals. As a consequence of the DTE protocol, as long as the quad rover is properly executing its mission, the communication session is uninterrupted. However, when the execution of the mission is interrupted, which is occurring right now as the rover is being picked up and carried to a different location, the rover will be unable to update or recover its cryptographic keys, and in this case the communication session will be lost. In terms of the software prototype, here I'm showing a basic view of the current software architecture. Our prototype is currently running in Docker. We've developed 3 containers, which I'll talk about in more detail soon, along with another volume that's used to share data across the containers. The Shared Data Hub is used for sharing data across the containers, including the mission plan, the public-private keys, and the sensor data recordings. The sensor data container is implemented through a series of ROS listeners subscribed to the rover's topic list. This data is converted into a pandas data frame, which is then pickled and saved as an ingestible Python object, as shown on the image to the right. The communication I/O container handles the key exchange and session information. This container implements a novel protocol that involves securely passing public cryptographic keys back and forth, which we refer to as the ping-pong protocol. Finally, the seed and key generator, in conjunction with the Shared Data Hub, handles the seed and key generation as described previously. Some of the salient features of our approach involve the following. First, encryption keys are never stored in persistent memory. In some cases, the UXS itself will be unable to decrypt its own data. When the mission is executing properly, however, the keys are recoverable, despite the fact that they are not stored anywhere on the system. Another potential attractive feature of the scheme is that our scheme can be modified to handle post-mission data, which is data that's encrypted in such a manner that it's inaccessible to the UXS for the duration of the mission and is only able to be decrypted after the mission has been completed. Thank you for listening to the information video for the Dynamic Temporal Encryption Scheme. For more information, you can either contact Ryan Gavris or Luis Martinez, whose information is included below.